computer. All right. So we're like 3/4 of the way to a major result. And so let me quickly remind you of where we were, what we were working on, and then we'll finish developing the result. So I believe we're in 5.3. I'm going to call it the fundamental theorem. Maybe we called it that on Monday as well, but today we're going to finish it. So remember the setup. We have some function. We'll assume it's non-negative. We start at A, maybe eventually working our way up to B, but we define this new function. We call it the area function and named it big A, which is the integral from A to X under the function. And we discovered right at the end of class on Monday that A primed of X is little f. Or another way of saying that is big A is an antiderivative of little f. Okay? And that's pretty much where we ended up. Of course, if little f has one antiderivative, it has infinitely many. So it's hard to know, like, which one is this? Which big A is it? So let's see what we can find out about it. First of all, notice these things. I think we wrote this on Monday. The function, the area function evaluated at the left-hand endpoint, what's that? 0. Yeah, there's the integral from A to A, there's no area above a point. So the value of A is 0. So we need an antiderivative of f that satisfies this condition. We'll see how we go about that. And notice that A evaluated at B is simply the definite integral, which I'm not sure I've been very clear about it, but our goal is to figure out what that definite integral is. I mean, we know the definition, the limit of a Riemann sum, right? And we actually worked that one time, but it was pretty complicated, even for a very simple function, x squared plus 1, if you remember. So we're trying to find a better way, a way that we can actually do if the function is more complicated. On Monday, we showed that, you know, if we could luck out and interpret the area under the function as areas we already know. We did semicircles and we did, you know, rectangles and triangles. We can get the value that way, but if we can't, like, what can we do? So our whole goal is to figure out what number is this? That's what's motivating us here. Okay, so I know big A is one antiderivative, but it's hard to know which one. So let's see, let big F of X be any other antiderivative. Then what we know is that they're the same then, except for the constant. All antiderivatives for the same function differ by a constant. Right? Because when we take a derivative, we lose that constant. Its derivative is 0. Okay, does that make sense to you? Now let's use what we know. Let's plug in x equals a. This is true for all x. So if we plug in a, I get that a, big A of little a. So let's say if x equals little a, well, that's big F of a plus the constant. This is 0, and so big F of A is the opposite of the constant that A and F differ by. Big A and big F differ by. Okay? If x equals B, then big A of B we're plugging in. I bet I have an eraser. Well, I plug in B to our relationship. That's what I get. And we know that big A of B is the integral. So another way of saying that is the integral from A to B, f of x dx equals f of B, big F of B, plus C. But if I multiply by -1 there, remember, C is the opposite of f of A. So think about that for a few seconds. How can I find the value of a definite integral? First, find I want the definite integral of a function little f. Okay. Right there, we say what it's equal to. I need that function big F. How do I get it? What is big F? It's an antiderivative of little f. Is it a special antiderivative? Okay, big A is a special antiderivative. But for big F, I said, I didn't raise the bar super high here. I just said, find an antiderivative. Any old antiderivative will do the job, right? So to find the value of the integral, first I find an antiderivative. I can find any antiderivative I want. And then I do arithmetic. I plug in B, I plug in A, I subtract. That's the value of the integral. That's the limit, as n goes to infinity, of the summation I equals 1 to n, f of x I star delta x. All I have to do is find an antiderivative, plug in the endpoints, and subtract. Okay, you should be rejoicing. It's a totally amazing result. It's called the fundamental theorem. I don't know. You guys don't look like you're rejoicing. I could make you not use it and do all of them by a limit of a Riemann sum. Would you like that, or do you want to use this result? Scott says it's this result.
Yes.
Yeah, absolutely. Some of you have been patiently, maybe not so patiently, waiting for us to learn this result. Okay, there's actually two versions of the fundamental theorem. I think we know both of them. Of the FTC, fundamental theorem of calculus. FTC. The first one is what we just derived. If big F of x is any antiderivative of little f, then the integral from a to b little f of x dx equals big F of b minus big F of a. It's pretty amazing if you think about it. There's a lot of information coded into that antiderivative. To find the area under the function f, I need an antiderivative, and I only need to know its value at two places, a and b, right? That's all we need, evidently. F of b minus f of a. So somehow, however f changes over the interval, affecting the area underneath it, all of that information is coded into the antiderivative. So all we have to do is plug in our endpoints and subtract. So I said there's two versions. I've written the first one. This is overwhelmingly the version that we're going to use, but every once in a while, we'll use the second form, which says this. If we define a function, I'll use the same language. It doesn't necessarily need to be area. if I define a function like this, and remember here we need a dummy variable because x is the upper limit. I don't want to use it in two different ways. Then a's derivative is little f. The second version tells us that differentiation and integration are opposite operations. Right? Clearly, derivatives and antiderivatives, that's opposite, but we're talking here about a definite integral. So how do when I define a function like this, when I take the derivative, it just cancels out. The derivative cancels out the integral, right? And we end up with just the function f as a result. So they're opposite operations, definite integrals and differentiation. Any questions? So the fundamental theorem says to find the value of an integral, a definite integral, what do I need first? An antiderivative. I heard at least two people say it at once. It warms my heart. Which antiderivative? Little f of x. Any antiderivative. Right? Any antiderivative will work. Which one do you think we should pick? What's the difference between two? The constant. So why don't we pick the one where is zero? Absolutely. Why would we do anything else? We're going to pick the one. Now you can pick whichever one you want. If you want the constant to be, the square root of 147 divided by pi times the natural log of 4, then you go for it. I'm going to pick the one where the constant is 0. Okay? We good with that? How do I evaluate an integral? First, find a. Now no one will say it. Thank you, William. Put a gold star on the top of your sheet. I think I'm worth talking to, aren't I? Find an antiderivative. So, and then we just do arithmetic. Right? Then it's just arithmetic. Plug in B, plug in A, subtract. What's the hard part of that process, potentially? What do you think, the hardest part? Is arithmetic hard? Well, you say, you won't give us a calculator on the test. But the arithmetic is always easy. If you have a calculator, is the arithmetic hard? No. So what's the hard part? If there is, maybe there's not a hard part, we can rejoice. If there is, what is it? Somebody talk to me. Finding the antiderivative, it all boils down to that. We get our hands on an antiderivative, and then all it takes is simple arithmetic. Now, if the function is the secant, and you got to plug in pi over 12, we can decide whether that's easy or not. If we have a calculator, it certainly is, but it's just an arithmetic problem once we find. So it all hinges on what is the antiderivative. And if we can't find an antiderivative, how does this theorem help us? Okay, but if we can't find an antiderivative, does this theorem help us? Not one bit. Not one bit. It's got to find an antiderivative. Okay? Are we good at antiderivative? Well, we're working at it. The last exam asked you to do 4 of them, right? The very first problem. And so, look at your score there, and you can tell like where you are. None of them were intended to be challenging. We don't really know any challenging ones yet, but we do have one more technique to learn. So to use the fundamental theorem, it comes down to finding an antiderivative. So we need to get better at that, and we will. We're going to take a look. I have one more class day after today. We're going to take a look at the chain rule for derivatives and see if we can work that backwards to get antiderivatives. But that's what it all comes down to. And when I say any, like I said, I'm going to pick the one where the constant is 0. You can do whatever you would like to do. That's what I'm going to do. For example, evaluate the integral I think this is the integral that we evaluated the definite integral by the definition. The limit as n goes to infinity, right? And we got an answer, and I think we got the right answer. But it took a lot of work, and maybe, maybe it took me leading the work we did. Yeah, maybe. I hope that doesn't sound like I'm bragging or anything. But I led the way. You guys maybe helped me, although you don't like to talk to me. And we eventually got an answer. Well, how do we get the answer now? Well, what do I need? An antiderivative. So here's the notation we write. So the antiderivative here on a scale of 1 to 10, 1 is like trivial, 10 is impossible. Where do you rate it? 5? 1, yeah, maybe 0, maybe -2. It should be -2, like piece of cake. So here's how we write the arithmetic. It's kind of weird, you'll get used to it. First of all, we write out an antiderivative. 1/3 x cubed plus x. Now we know the definite integral is equal to a number, not a function, so I have to do something that shows there's some arithmetic. We draw a straight line. I think we've done this before. That line is the words evaluated at. And some of you may have made your line actually have little tabs on the top and bottom. You'll see that sort of thing every now and then. It doesn't matter to me. And then we write our limits. So the lower limit, I'm going to write there. And we don't usually write it. If we need to, we can do it. Like if there's more symbols involved here, we could say, like, these are x values. Because x is the variable, the limit, and the integral goes from 0 to 3. And then we just plug our values in. So 3 cubed plus 3 minus 1/3 0 cubed plus 0. And you could probably see we were going to get 0 there. And we don't need to write it out if it's going to be obvious. So this is 27/3 plus 3, which makes 12. So even with me jabbering away, it only took us about a minute and a half to do it, whereas it probably took us 15 minutes to do it by the definition. So, the fundamental theorem, it sounds important. Fundamental theorem, and it is super helpful. If we can find an antiderivative, totally useless if we can't find an antiderivative. Part B, the integral from 0 to 4 e to the x dx. Anybody know an antiderivative? E to the x. And then we draw our bar, and then we put the values. Now, something interesting, something happens here, we need to be careful. So plug in 4, I plug in 0, subtract. And what's the answer? Yeah. Sometimes it's tempting that if the limit is 0, we just think, well, the function's going to be 0. And some functions are, but some aren't. E to the x is one of them. Exponential growth, we're going out to 4, and we just calculated that the area right there is u to the fourth minus 1. U to the fourth is probably around 70, maybe, rough estimate. So the area is around 70 units of area. Part C. The integral from 0 to pi sine x dx.
So the derivative of sine x is negative cosine.
You agree? Perfect. Negative cosine of x. From 0 to pi. When I have a constant in front of my whole antiderivative, I'm going to pull it out. And then I'm going to deal with it at the end. So you don't have to do it. You can leave it in there. I think it has a tendency to create sign errors. Certainly need to be careful. Cosine pi minus cosine 0. What's the cosine of pi? Anybody know? And the cosine of 0? So plus 2. The value of the integral. 2, which is sort of interesting. Take the sine wave. We just found the area in one little bump of the sine wave, and what we discovered is there's exactly 2 units of area in there. Okay? Certainly not obvious, but true. If you're in my Calc 2 class in the spring, it's a good thing to have memorized because we're going to run into it every now and then. And it's kind of good to know that there are 2 units of area. Part D, the integral from 0 to 2 pi. Can you tell me the value of this without calculating? Matthew said 0, right? Can you explain that to us?
1 pi is 2 on the top, and it's another pi is 2 on the bottom.
Yeah, the sine function dips down in the x-axis. We know the integral function's not negative. It tells us the net area. And so Matthew believes we all believe, we just calculated, there are 2 units of area in that first bump, but then we reproduce that bump below the x-axis, right? And is it easy to believe there are 2 units of area in that thing? But they're below, and so we get 2 plus negative 2. We do get 0. Now, you could find an antiderivative, you could plug in the limits, and you'll get 0. We're just taking advantage of some things we know about integrals and also about the sine function. E. 1 to 5, 1 over x dx. Looking for that area.
So the derivative of 1 over x is ln of the absolute value.
Yeah, ln of the absolute value. Evaluated from 1 to 5. Is ln 5 minus ln 1. 5 and 1 being positive. So the absolute value sign not needed. What's ln 1?
It's 0.
It's just 0, yeah. So ln 5 is our answer. Probably about 1.4-ish, maybe. We'll just leave it as ln 5. Certainly, if this is on the exam, that's our answer. It doesn't matter. Decimal approximation, we don't really care. ln 5. Any questions? How about F? The integral from -3 to -2, 1 over x dx. Let me draw a picture. Now we have the same function, 1 over x, but now we're in negative territory. So we get the other side of the hyperbole. We go from -3 to -2. So what kind of a number is that integral going to be if we do the work correctly? It's going to be a negative number. Yeah, the area is down below. And notice my limits, the smaller number is on the bottom. -3 is smaller than -2. So that everything's lined up there. If those were backwards, that would change the sign, right? So that's not happening. And now you can see here where the absolute value signs are absolutely necessary because I can't plug negative numbers into the log. And so we get ln2 minus ln3. The absolute value sign knocks the minus signs off, so we can plug them into the log function. Questions?
Isn't the difference of 2 logs the log of the quotient?
It is. So another form of that answer is the log of 2/3. Either one is fine with me. I don't know if one is better than the other. I guess if you like one better, that makes it better. G. The integral from -2 to 2. One over x squared plus 1. Yeah.
At the one that took up one, that the derivative of the right-hand function.
Yeah, so I think William's suggesting the antiderivative is the arctan, the inverse tangent. We agree? Yeah, absolutely. The inverse tangent of x. Evaluated from -2. I'm going to evaluate this 2 ways. First way, just sort of brute force, straightforward, and then we'll talk about it just a little bit and realize savings. Can I change this from -1 to 1 just because we can get a better answer? Of course I can, I'm the teacher. Inverse tangent of 1 minus the inverse tangent of -1. The angle whose tangent is 1, what is it? Pi over 4. The angle whose tangent is -1. Yeah, negative pi over 4. So we end up with, I'm getting ahead of myself. Pi over 2, half a pi is the value of. Okay? So that's sort of brute force. Here's another way to do it. And, involves a little bit of a higher level of thinking, but it's, I encourage you to think about this, and we'll see it again from time to time. And we'll try to take advantage of it when we can. So, yeah, the function we want the integral for, 1 over x squared plus 1. I don't think we've ever graphed it before. And so, like, it shouldn't just be like sitting there on the top of your mind, just ready to roll out. But if you think about it a little bit, it's always going to be less than or equal to 1, right? Isn't the denominator always bigger than the numerator? I mean, the numerator is 1, the bottom starts at 1, and then we add a positive number onto it. Right? So the function is always going to be less than or equal to 1. Can it ever be equal to 1? We're talking about the function 1 over x squared plus 1. Is there any x that makes it equal to 1? Yeah, 0. Okay, so it's at x equals 0, it's 0, and then it, for all other values, it's less than 1. What's the limit as x goes to infinity? Yeah, how about this? It approaches 0 because numerator and denominator are polynomials, the degree of the top 0 is less than the degree of the bottom 2. Right? And that's a theorem we know. It's going to be 0. So it peaks at 0, and then it just sort of dies away. Because the only power of x is an even number, it doesn't really matter if I plug in a positive or a negative number. I'm going to get the same functional value. Right? Maybe in high school you learn to call that an even function. This function satisfies what you give it a name f. That f of x equals f of minus x. A function with that property is called an even function. Maybe because for polynomial type functions to have it, all of the powers have to be even numbers. For us, it means like take 5, take -5, the values are the same. So the graph is symmetric across the x-axis. And finally, I'm ready to evaluate this integral a different way. I'm going to take advantage of symmetry. I'm only going to integrate from 0 to 1. I love 0 as a limit. It makes the arithmetic so easy. And then I know if I can find the area here, it's going to be the same area. So whatever value I get, I'm just going to double it. Take advantage of the symmetry of the function, simplify the integral, and double it to get the answer. So now we get twice the inverse tangent of x from 0 to 1, which is twice the inverse tangent of 1 minus the inverse tangent of 0. I think William just told us the inverse tangent, the angle whose tangent is 1 is pi over 4. What's the angle whose tangent is 0? 0. Guess what we get? Pi over 2. Do we like that answer? Absolutely. It's what we got the first time. We better get it again. But someone's giving you bad information. Any questions? How about this one? A, B, C, H. The integral 0 to pi over 3 secant squared theta d theta. We all know, I'm not sure how much we've done with it here, if any, but a lot of times when trig functions are involved, we use theta as the argument instead of x, theta being kind of a generic angle symbol. So, it's what the d theta, the d is there for, to tell us what's the variable. So if we have d theta, then we're just going to interpret theta as a variable. Anybody know a function whose derivative is secant squared? Yeah, we all do. Tangent 0 to pi over 3. So we get the tangent of pi over 3 minus the tangent of 0. Anybody know the tangent of pi over 3? Square root. Somebody knows I know. Square root 3. Tangent of 0. Zero. It passes through the origin tangent. Okay, questions? Square root 3 is our answer. In this section in the textbook, there are 20 definite integrals for you to work out. Some of them are implemented in the online homework. I'll make some of them part of the assignment. But in the end, You should know how to do all of them. All of them should have a fairly obvious, if we understand where we are, antiderivative. And so find that antiderivative and do the arithmetic. So there's no shortage of problems you can practice on. I can post the page number. It's in section 3, chapter 5, section 3. You'll see them if you look in the book there. All right, so I don't know the section number here. 5 point something. We're going to talk about expanding our ability to find antiderivatives. That's what the whole fundamental theorem hinges on. Being able to get our hands on an antiderivative. If you remember, in class on Monday, we were able to evaluate integrals like this by recognizing the function, the graph is a semicircle, and then we could use geometry. But now we say, well, let's just do it now by an antiderivative, but guess what? We don't know any function. It's beyond the scope of our ability to find an antiderivative of the square root of 4 minus x squared. So even though we have a super powerful fundamental theorem, it doesn't help us for that integral. It doesn't help us on any integral if we can't find an antiderivative. So that's where we need to work. That's the weak link in our ability to evaluate integrals. We're good at arithmetic. It's that antiderivative. But like I said before, there's one derivative rule that we haven't really investigated yet that's really going to help us expand the kind of functions we can get antiderivatives for, and that's the chain rule. In Calc 2, you'll take a look at the product rule for derivatives and you'll get some good information out of it. It's not a product rule for antiderivatives. I've told you before, there is no such thing, and that's true theoretically. Never ever will we learn a product rule for antiderivatives because there's not one. But we'll be able to use the product rule to get some information. Your Calc 2 teacher will explain that to you. But I want to take a look at the chain rule. So remember, chain rule works on compositions. And it tells me the derivative is we differentiate the outside function. And then we multiply by the derivative of the inside function. So interpreting that as an antiderivative, it's a little bit clunky, but I can write it. If I ever run into a function that looks like this, f prime of g of x times g prime of x, what's the antiderivative? F of g of x. Absolutely. Plus any old constant. So notice what happens. In order to have the form we need to get an antiderivative fact out of this, the inside function, its derivative, has to be sitting there. But it goes away because, you know, it's not over here. It got kicked out as a result of the chain rule. The other sort of subtle thing that happens here, notice on the left we have an f prime over here, and over here we have just f. So to go from here to there, first of all, I have to make sure this is the form we have. And then I have to say, what is that function f? And I need to anti-differentiate it, right? That's how we get rid of the prime. This is f prime. This is f. Okay, simple example. And then we'll get a little more interesting. Evaluate. For the time being, we'll just focus on the antiderivative. We won't do definite integrals. So here's the first one. Starting out super easy. Now let me write it differently. been teaching calculus for over 40 years. I've probably had 100 sections. And based on my experience, this is tricky. So now, we know exactly what we're doing. We know the chain rule, so we can figure it out. But we need to make sure what we're doing is based on solid facts that we know. So we're going to think of that guy right there as f prime to g of x. That's a composition. And how do we think of 2x? Well, here's our g of x. What's the derivative of g of x?
X.
Yeah. So man, this problem is tailor-made for the chain rule. It's like I have a composition, and sitting there right by the composition is the derivative of the inside. So what do? I need to integrate, anti-differentiate the square root sign. Well, how do we do that? We think of the square root as the 1/2 power, raise it by 1, divide by the new power. So here's our answer. I'll write it in exponent form. The power is now 1/2. We're going to raise it by 1. Divide, or what we've been doing is invert and multiply when the power is a fraction. Plus any old cost. We have the perfect form. F of g of x times g prime. And all we have to do is integrate it.
Is it possible to integrate a composition that's not in this form?
Well, we have to get it in this form. The answer is yes, but we have to do legal things that we've identified as okay to do to get it in this form. And maybe you're thinking of a particular thing we can do. Are there any questions here? Matthew?
The 2x, you can do it times 2x.
Okay, so 2x playing the role of g prime and doesn't show up over here. Any other questions? Okay, does it seem a little bit odd to some of you? Like, is there some way you could check it out? Is that really right? How do we check it?
Find its derivative.
Take the derivative, see what happens. Let's do it. We're not going to do this every single time. On the next 2 exams, we have one next week, we have a final. If you have time at the end, then there are going to be some antiderivatives, so check your results. If you feel good about them when you're solving it, maybe you can save the checking for later and make sure you have time to do it. Here we go. I want to take 2/3, 1 plus x squared to the 3/2 and calculate its derivative. Of course, I'm going to have to use the chain rule because it's a composition. So dy dx. The first thing we're going to do is pull the power down, and what does it do immediately? Yeah, it wipes that thing out. We're not surprised by that because we invented that number, 2/3, to do precisely that. Okay, and then we have 1 plus x squared. So what power? Taking the derivative, you remember those, the good old days. Times derivative of the inside, 2x. So let's write the 1/2 power as the square root. So does it check? Absolutely. Perfect. All right. Now, let me explain this word substitution. What we're really doing is reversing the chain rule, but everybody calls it integration by substitution because here's the way we're going to think. We're going to try to simplify it. We have f prime of g of x times g prime of x dx. And there's a way we can simplify this to kind of avoid recognizing it as a composition, at least initially. So, you've seen before, we've used this notation, dy dx to represent a derivative, right? And I didn't do it then just because of right now, but I'm so glad I did. Like there's a fresh reminder. And so far, we have not defined the dy and the dx separately. It's just like one symbol that means derivative. Well, now we're going to define them separately. So we're going to define dx is just a number. It's probably a small number, but we're never going to care about what the number is. We just want to think, we can think of it, treat it like it is a number algebraically. And then I'm going to define dy. I'm going to define it so that this turns out to be true. That is, it's equal to f prime of x dx. And in the background here, y is the function of x. These quantities are called differentials. The differential of x and the differential of y. And I think we have just enough time to work this out. So we're going to take this thing, and what I want to do is simplify it. So I'm going to change the variable from the original variable x to a new variable. I'm just going to make it up u, and I want it to be the inside part of a composition. So symbolically, it's g of x. Now, I need to know how u's differential compares to x's. And so immediately, u is a function of x, so its differential is the derivative. So then that guy becomes f prime of u, and then g prime of x, that's du. Plug a u in there. And we've simplified the integral. We've temporarily, at least, eliminated the composition. So if I were to work this thing out, I would let u be 1 plus x squared. And du is 2x dx. So I get the integral of the square root of u du. We've reduced it to an antiderivative that we learned earlier. And then I would find the antiderivative in terms of u, and then substitute back in the original relationship. Everywhere a u shows up, I'm going to write a g of x. All right, sorry to rush through that. I'll give you lots of homework problems to work on. And we'll do some more on Friday. See you then.